So without further ado, I would like to explain to you a question that I often get quizzed about in the RASC, in our community of amateur astronomy enthusiasts and observers. I often get teased because I always manage to bring the conversation around to globular clusters. So folks ask me what's so special about globular clusters. And so it turns out I actually have a few things to say on that topic, and I'd like to do that right now. As you see, this is Messier 75, one of the kind of classic list of globular clusters that folks look at. And, you know, it does have that sort of standard look. Anybody who's been interested in astronomy for longer than about 2.5 minutes knows that a globular cluster looks like this. Lots of stars concentrated towards the center, pretty much a round shape. Therefore, we kind of figure they must be more or less spherical. And they are considered among the most beautiful of the objects that we admire in astronomy. This picture is by the Hubble Space Telescope. And of course, again, that's not a surprise that the HST leads the way in taking beautiful, inspirational photos. But I'd like to start by just summarizing some of the history of globular clusters. They are, of course, a very active topic in modern scientific research, but it goes back an awful long way. And in fact, the astronomer in ancient times, known as Ptolemy, actually observed the object Omega Centauri and called it a star in the cloud on the horse's back. I'm not sure what horse he might have been referring to. I'm not so sure that what the ancients thought of as constellations or star patterns is really all that important to our understanding of astronomy today, but certainly the history of their awareness has, at the very least, some philosophical implications and philosophical weight to it. So the fact that Ptolemy made some kind of a record of the object Omega Centauri is at least a good point to start with. Whether it was observed before that, of course, we probably have no record. And basically the topic of globular clusters has sat there with no progress at all until something like the 18th century, when Edmund Halley first kind of categorized things and wrote of M13, that the deep sky objects and M13 and other deep sky objects must be, incredibly distant and incredibly large, and there must be tremendous vast things out there. And so, this is something that folks gradually came to appreciate. And I don't know, I always find myself coming up short when someone asks me about trying to comprehend the size or scale of things in the universe. And the bottom line is, especially because I spent my career as a math teacher, I don't really think there is any way for us to visualize sizes and distances in astronomy. I think we are forced to resort to some basic understanding of math, and I might even dare say it's arithmetic, because if you know how to do exponents and multiply things by 10, that's at least gets you started. And that's how we do these things. And so for globular clusters, we need to take it for granted that we can toss powers of 10 around and get familiar with our universe that way. So then a little later on in the 18th century, everybody knows about the Messier list. I already mentioned one of the Messier objects in my opening slide. And of course, without really understanding what they were, what their significance of them as a category was, Messier included quite a few globular clusters. And I'll make a few other remarks about how significant the globular clusters are in Messier's list as we go on here. And then William Herschel, who, let's face it, Messier had a reputation as a comet hunter, but his telescope was fairly small. And William Herschel really went far beyond what Messier had conceived in terms of cataloging the objects in the sky. So in fact, William Herschel probably gets credit for discovering almost all of the globular clusters that we would consider on our modern list, at least those in the Northern Hemisphere, because of course he was located in England. And in fact, it was his son, who was an equally famous astronomer named John Herschel, who first came up with the term globular cluster. And John Herschel, of course, spent time in the Southern Hemisphere and discovered many of the other globular clusters that his dad had not discovered. And another thing I find interesting about John Herschel, we often see a symbol, a circle with a cross in it, that is used to represent globular clusters. I can't explain why the same symbol is sometimes used for the Earth in lists of things where planets in the solar system get symbols. the Earth has the same symbol as what a globular cluster is. And I don't know why that is. I've tried to keep that in mind as I look for things, but I've never come up with an explanation for that. The southern globular clusters that I was just mentioning, William Herschel and John Herschel, the southern globular clusters that were not discovered by John Herschel were mostly discovered by James Dunlop, who sort of beat Herschel to getting down there. And he was in Australia, and he had again a fairly modest telescope. And he did discover a handful of globular clusters from the southern hemisphere. It does, on my slide here, it says that he recorded some 629 separate objects, and many of them were not verified later when folks went to double check on these things. So probably just because he was ambitious and was using a modest telescope, he made an awful lot of what we would today frankly call mistakes. But he does get credit for 21 of the globular clusters that are visible in the southern hemisphere and had not been recorded before that. So by the time we get to the late 19th century, we really had no real physical understanding of what the globular clusters were, just the location of them on the night sky, basically. And we didn't realize at the time, scientists in the mid to late part of the 19th century didn't really realize that there was a reason why the list of globular clusters didn't continue to grow as discoveries mounted. So more open clusters were being discovered, more of the galactic nebulae were being discovered, more of the planetary nebulae were being discovered, but the list of globular clusters didn't continue to grow. And we didn't appreciate that until the 20th century kind of got rolling. And kind of what got the story rolling was the story of Solon Bailey from Harvard University, who was at the observatory in Peru. That observatory has since been moved to South Africa, but Solon Bailey took photographs of globular clusters there and actually literally counted the stars. He literally made a grid on the photograph and then counted them. And so he was really the first person to have an appreciation for this modern superlative that folks often mention when they look at or show a globular cluster at a public star night or something. The globular clusters contain hundreds of thousands, maybe even 1 million stars, which is part of the reason why they're so stunningly beautiful. Well, Solon Bailey kind of started that off by actually counting them. And, he didn't get anywhere near the 100,000 mark, but he certainly did appreciate that there were tens of thousands, and the number just kept growing as time went on. Then there's another famous twist to this story in the early part of the 20th century that relates to an astronomer named Henrietta Swan Leavitt, who worked with variable stars. And what she discovered was that you can measure the variation of a variable star quite easily in time. In other words, you make a note when it's brighter, and then it gets dimmer, and you make a note when it gets brighter again. You don't need to know much about the actual brightness to see that it's gotten dimmer and then brighter again. And so the periods were fairly easy to observe. But the actual brightness of them had to wait until the scientists were able to determine how far away they are so that we could tell how much the bright light from them was dim due to distance. And so by the time we get into around 1910-ish, Henrietta Swan Leavitt had enough data on variable stars that she was able to demonstrate that certain categories of variable stars follow a rule where the brighter they are, the different brightnesses that they show, the different brightnesses that they actually are known to emit can be correlated to how long they take to vary. And so this gives a really interesting opportunity, because what you can do is you can go out beyond, once you've got the relationship established, you can then go out beyond where the list of the stars you studied to make the relationship, and you can measure the periods of other stars and put them on the relationship, and therefore know how bright they really are, calculate backwards to tell where they are in distance from our solar system. That was really important because it really gave, for the first time, a sort of a ladder of allowing us to measure more and farther and farther away from home here. And basically got the 20th century on a solid footing for measuring distances and the scale of the universe in its entirety, which of course was really quite a spectacular thing. And again, it's useful to emphasize that this is just barely 100 years ago. Before that, any estimates of distance and so on were very uncertain and quite unreliable. So using the information and the studies and all the data and the calculations that Henrietta Swan-Leavitt made, the astronomer Harlow Shapley at Harvard studied the globular clusters in particular. There were variable stars in the globular clusters, and it's reasonable to think that, you know, the globular clusters look like they're pretty far away, but probably within a globular cluster, the closest star is probably not that much closer than the farthest star. So they're all more or less at the same distance. So if you can figure out the distance to one star in a globular cluster, you more or less know the distance to the globular cluster. And so what Shapley did was he did this for a whole bunch of the globular clusters that he could observe back then. And so the chart that you see here was published in 1918. It uses arrows to give a vertical measurement above the page. And what he found was that the globular clusters seem to be centered on a place, a spot in space, which is not our solar system. This was really the first direct evidence that we had that our solar system is not at the center of anything we'd ever imagined or conceived of. So in a way, this was kind of the Copernican equivalent for stars and what we now think of as galaxies, where Copernicus, of course, did that for the sun and the solar system. It's really neat. And so the sun, our solar system, is quite eccentrically located outside of the general system. The general system that Shapley's referring to, of course, didn't really distinguish 100 and change years ago between just our galaxy and the whole rest of the universe. That came very quickly shortly thereafter. And this is actually an interesting RASC connection. John Stanley Plaskett was a president of the RASC and a professional astronomy researcher at the Dominion Astrophysical Observatory in Victoria. And he also studied variable stars and globular clusters. And as far as I can tell, sometime in the mid-1930s, he was the first person to kind of think that it would be a smart idea to draw our galaxy in a side view like this. I cannot find any earlier drawings in any published research anywhere that that show the galaxy drawn this way. We recognize, of course, the Milky Way galaxy with its disk, the bulge in the center, and then all those white fuzzy dots that are sprinkled around are, in fact, the globular clusters. So the globular clusters, even though they're centered on the Milky Way, they seem to be not in the disk and the bulge of the Milky Way galaxy. Something special is going on there. And that really makes them kind of interesting from a physical point of view. And of course, I'm also interested in the philosophical aspects of this, what it does to our sort of human spirit to know that we are, you know, going out further and further in our understanding. We generally need telescopes to make these observations. So I thought I would tell you a little bit about my own background. My parents gave me a telescope like this, a 30mm aperture telescope for the holidays in 1966. And I thought I died and gone to heaven because I thought I'd now be able to see all those wonderful things that were in the photographs and the books in my school library. And of course, a 30mm telescope isn't going to show you, you know, the Dumbbell Nebula in glorious color. And so I got a little bit frustrated with how flimsy this thing was. And I should have blamed myself. I should have said, all right, I need to develop my skills. And it took a long time for me to realize that, you know, you got to really work hard at being a good observer of the night sky. And someone like David Levy has, you know, a lifetime of observing. I didn't really get that for a while. But what I did get was a real interest in science fiction. And I did find a few references to, in some of my favorite science fiction stories, there were globular clusters mentioned, or something like globular clusters. And here's a passage that you're reading right now, I'm sure, from the short story or novella called Nightfall, which was published by Isaac Asimov in 1941. And it's set in some kind of a cluster. If I remember correctly, and I haven't reread the story just looking for this specifically, but he doesn't specifically say what kind of cluster it is. Anyway, there's thousands of stars around this planet. And there's a combination of eclipses. That means once every 1,000 years, there's actual darkness. And then they see, the folks living there see all this wonderful backdrop of thousands upon thousands of stars in their sky, which would be a very impressive sight, especially if you only saw it once every 1,000 years. So I remember kind of getting my, the little hairs on my 12-year-old neck were standing up when I read this story, and it just thrilled me. Another novel that I found, this is a juvenile novel called The Star Conquerors, and in it some nasty alien creatures try to attack the poor human beings in the solar system, and the human beings respond by raising up an enormous army and heading out to hand those nasty invaders a good whipping. And the nasty invaders have their home planet in a globular cluster. And what I remember about this book, which is really, really cool, is that they have a star map in the navigational deck of the main admiral's star cruiser on this massive fleet that's going out there to win the battle for the humans. And this star map is in 3D, and the picture of the globular cluster is described so beautifully in this book by Ben Boba. And again, I was just kind of mesmerized by the concept of it and so on. And I kept that, and that sort of stayed with me. So eventually I got into high school and figured out a little bit more about telescopes. And this is the 15-centimeter Newtonian telescope that I built on a pipe mount, according to the design described by Sam Brown in the book All About Telescopes. And any of you who are babies born in the 1950s or perhaps even earlier than that will probably remember that book, because that was what all of us used as youngsters to either dream about telescopes or go ahead and actually build one. I didn't grind a mirror myself. A lot of folks asked me about that. The mirror, I just bought the mirror from Edmund Scientific, but the tube and all that stuff was assembled according to the designs there in the book. And I managed to see a few things with it, but I have to admit, in my last few years of high school, I was concentrating on other things and didn't bother to start developing any skill. I came to London in 1973 and was a student at Western University. I stayed in London here, and all these years since then, my wife and I live in the suburb of London, and we're not too far from the university. And I've been volunteering at Western's University for most of that time. And this is their big telescope at Elginfield, which is about 40 kilometers north of London. And this is the business end of the telescope. In fact, the night that this picture was taken was actually an open house. After some 40 years, this was the first time they ever had an open house to invite the community in. And it was on the occasion of them basically closing down the research at the telescope. The telescope is a 1.22 meter Ritchie-Chrétien design. And, by the time you get into the 21st century, all of the research faculty at Western were using, big telescopes on mountaintops and participating in grand collaborative schemes with Hubble Space Telescope and so on. And they just found it wasn't worth it to keep using the Elginfield telescope. So it's been mothballed. So there's a 1.2 meter telescope sitting outside of London, and it's not gathering any photons right now. It's just gathering rain, really. And I'm sure there's mice and so on inside there. But this was the night of the open house. And it's important to me because I did spend one summer as a summer student there. And I'll say more about that in a minute. So I mentioned the variable stars in the globular clusters. This is a slightly animated image of Messier 3. And if you look at this, you should see a few of the variable stars brightening and dimming. This is an animation. I don't think it's a long period. I think it's just a short loop that just shows some of the variable stars getting brighter and dimmer. And this is what a scientist would have done for the most of the 20th century to study globular clusters, is work on the variable stars, trying to figure out, first of all, their periods, figure out what categories of variable stars they are. And then over time, and this becomes important for me in my connection to the globular clusters, the periods of some of these variable stars actually change a little bit over decades of time. And that is important in unraveling what we can learn about the development of stars in the globular clusters. And so learning something about stars themselves and the nature of stars. So my story connects to the globular cluster NGC 5897, which is in the constellation of Virgo. And this is a picture of it by the Hubble Space Telescope. It looks lovely because it's a Hubble Space Telescope picture. But if you look at it through a modest to medium-sized amateur telescope, you won't really see much. It's just far enough away and it's kind of dim enough that you don't get that sort of impressive view that you see when you look at Messier 75 or one of the other famous globular clusters. So I got involved with this because the summer I spent as a research assistant during my undergraduate years, which was the summer of 1975, I worked for a professor named Amelia Waylau, and I'd like to dedicate this slide to her memory. She passed away last year, and she had studied the variable stars in these globular clusters through the 1950s and 60s and into the 1970s and 80s, in fact. And she retired sometime in the late 1990s, I think. And she worked with famous Canadian astronomer Helen Sawyer-Hogg, who basically made her entire career and made her fame on the study of these variable stars. So what you see here is our finder chart that we used in the summer of 1975 for the variables in NGC 5897. The stars that are labeled with V numbers, V7, V6, V3, so on, those are the variable stars. They have been identified already 20, 30 years before by Helen Sawyer-Hogg and others. And then the ones that are identified by letters are the standard stars whose brightness had been measured very, very carefully with detailed studies. And so we were going to compare the brightness of our variable stars in many, many pictures to these standard stars, and then put their time, the time of their observations, in other words, the time of the photograph, into a calculator program and calculate the period of these variable stars. And so for NGC 5897, Professor Waylau and the other folks who studied these found it very difficult because it's obscured and there's only a handful of them there. And they weren't able to get really good period studies at the time I was a student. So basically the work I did that summer using glass plates that were taken both by us at Elginfield using the telescope that I showed, and also from plates that we'd gotten shipped to us from the University of Toronto's observatory down in Chile. The measurements I made over that summer basically ended up having too great a variation in precision and so on, and really didn't give the secret. It wasn't until something like 15 years later, David Levy and I were up at Mount Lemmon in Arizona, and we were there for overnight, and we stayed for the next overnight. And during the afternoon, I thought, well, I'm not going to be bored sitting here. So I started, sure enough, they had the entire collection of the Astronomical Journal in the library at this observatory up there on Mount Lemmon. And I kept looking through it until I found Professor Waylau finally published the periods of the variable stars in NGC 5897 in 1990. So it took all that time, all that data. And sure enough, if you look at the very last paragraph, the last paragraph is here, and it says that Professor Waylau acknowledges the help of many student assistants. You know what? I was one of those student assistants. And this was my one chance. This is as close as I've ever come to contributing to astronomical research directly. I am mentioned as one of the many students at the end of this paper. Well, here's how I did it. They had a machine called the automatically balancing electronic variable iris diaphragm photometer, which had been invented way back in the late 1940s. And they put fairly, what was in the 1970s modern electronics on it. And what you did was you took a glass plate, and put it on the stage at the top of this device, and it shone light through it and through mirrors. You got an image of what was on the plate in front of you, and then you moved the plate around because it was on a stage that turned, that moved back and forth. You moved it until you had this ring in the middle of your machine that was centered on a star you wanted to measure. And then inside the machine, there were electronic circuits that changed the size of this iris, which you can see in the picture here. That iris would change automatically in size to come to a standard value. And the standard value is what I would then write down. So I wrote down the standard values for all of the known fixed brightness stars in the cluster, and then all of the variables we were studying. So I would make a plot, and the plot would show how bright stars were as a function of these measurements that we were making on the photometer. And then you would put the variable stars on there, and that would tell you their brightness at the time of that photograph. And of course, this is totally done with a piece of graph paper and a sharp pencil and a curved ruler, a French curve. So it didn't have any of the mathematical complexity that would go into doing this today with a computerized photometer. And so, of course, that really was the key difference. Nowadays, these measurements are all done with CCDs that feed computers, and all the data is measured that way. So if you want to find globular clusters, and eventually I got keen enough on this, I thought I'm going to figure this out. This is what you look for. There's that same symbol, the circle with the cross in it. You look at Sky and Telescope's Pocket Sky Atlas, and all the globular clusters look exactly the same. They all have this exact round yellow circle, and the only difference is their sizes, which in the Pocket Sky Atlas is supposed to give you a hint about their brightness, but really it's very misleading. If you flip through the Pocket Sky Atlas and just look at all these yellow circles, you might think you're going to just sort of, oh, you've seen one, you've seen them all. But of course, every globular cluster has something interesting or unique about it, and they don't tell you that in the Atlas. You've got to hunt that down for yourself. It's a really interesting project to do. And one of the ways to start this, especially for novice amateur astronomers, let's say if you've started working on your Messier list, you're going to encounter some of these globular clusters. One of the things I thought was really kind of cool, I noticed that if you wanted to, you could group the globular clusters into little triplets. And so I like to call this Goldilocks and the three globulars. And this is in the constellation of Hercules. There's the globular cluster M13, which of course is very, very famous. And it's in the keystone of Hercules. And then a little further up, which depending on how you view Hercules, a lot of folks view Hercules standing upside down, so the head is down towards the south. If you view it that way, then there's M92 and NGC 6229 between Hercules' knees. And the three of them make a really tremendous comparison. M13, of course, is blazing and it's famous. M92 is well known, but it's a little smaller, still very beautiful. And NGC 6229 is almost always forgotten when people talk about their favorite deep sky objects. So I would like to recommend that if you think this is worth doing and you want to take up the globular clusters, this is the kind of thing you want to do. This is an approach you can take. Go ahead and start with one like M13, move to M92, find out what the third one is in the group, 6229, and then gradually work your way through the list like this. It's a really rewarding thing, lots of fun to do. And if you'd like a little more detail on this, Ken Hewitt-White, who lives in British Columbia, many of you might know him, wrote about this in Sky News in 2009, and basically took the exact idea of looking at these three globular clusters and kind of linking them together as an observational experience. I've actually gone and done this with a bunch of different constellations or different areas of the sky, where three globulars that nicely fit together can be viewed, within a few minutes, back and forth like that. I liked it, for instance, I refer to my friends the Scorp trio, which is in the constellation Scorpius, the famous M4, Messier 4, which is actually one of the closest globular clusters at only 14,000 light years. And it's quite a famous object. But then you also have M80, which is a fair bit further away, and yet it's very compact. Maybe you would expect it to look smaller. It's actually still pretty good thing to check. And then NGC 6144, which is actually a little closer than an M80, and yet looks much bigger, looks almost the same size as M4, but it's much more sparse. Makes a great target if you're working your way up to more difficult observations in amateur astronomy. That's a kind of a neat way to approach this. And these three photos were taken by my friend Steve Barnes, and I deliberately asked him if he to explain this to me, and in fact, at least one of them was actually taken for this project. He took them all on the same scale with the same exposure, so that you would kind of get some sort of a sense of the comparison in this slide. The comparison is really obvious if you look at it with your eyeball through your telescope, but it's not so obvious if you look at encyclopedia or catalog photographs of these three objects, because when they show them in a catalog, they adjust them to make them look all the same, which I think kind of defeats the purpose. Well, there's all kinds of globular clusters around the sky, and you have to go to the southern hemisphere to see a bunch of them. Some of the most famous ones are down there. In 2010, I had the great opportunity to go down to the Atacama Desert with Steve Barnes and some other friends. And this was one of my favorites. I didn't take this photo. It's a really lovely photo. There's this great dark nebula, which is nicknamed the Dark Doodad. This is just south of the Southern Cross. Can't see it from up here, of course. And it's a fairly well-known feature. So a lot of folks look at the Dark Doodad, and then some folks might even kind of overlook the fact that there's this really glorious globular cluster at one end of the Dark Doodad. If you're in the Southern Hemisphere, or if you're planning to go down there, and you're making a sort of a bucket list of things you want to observe, put this one on your list, because that's a really, really cool observation to make. So let me also mention, in the same breath, when I talk about the southern globular clusters, almost everybody wants to talk about 47 Tucanae, which happens to be located in the sky more or less in the same direction as the small Magellanic Cloud. The small Magellanic Cloud, of course, is separate from our Milky Way galaxy. It's not as far as the Andromeda galaxy, but it's separate. And I think a lot of folks probably make the mistake of thinking that 47 Tucanae is in the small Magellanic Cloud, but it's not. It just happens to be in that direction. It's less than 1/10 the distance of the SMC. So you see 47 Tucanae quite prominent in this slide, and you see the SMC, but you also might notice at the very top under the letter E in the word Magellanic, there's one of the globular clusters that is actually located in the SMC. There's something like a dozen globular clusters in this photo that are all, much, much farther away than 47 Tucanae, but they also make interesting targets. You've got a big enough telescope down there in the southern hemisphere, you can really go through these things. Again, it's a very rewarding thing to do. Nowadays, I've graduated from my 30mm floppy mount telescope of 1966, and I'm using a 40cm Newtonian with a Dobsonian mount built by my friend Mike Haynes with a low profile design. This has gotten to be fairly popular nowadays. When Mike designed this back in the 2005-ish, we built this in 2009, this was still a fairly new idea, and I really love this design. It's handy. It can be taken apart, and in fact, I have it sitting next to me here in my office, and my wife and I often drag it out to the trunk of our car and take it out for observations. We've even had it out for public observing sometimes. So it's a very neat, convenient design to use, especially for a telescope of 40 centimeters aperture. Really makes it quite useful. So if you decide to take this on, the next question you're going to want to ask, of course, is where can I find a list of all the globular clusters to view? So it turns out that since the globular clusters are associated with the Milky Way galaxy, and we more or less know where pretty much all of them are, there's only something like 160 globular clusters in the entire Milky Way. This is really neat. I found this really interesting because I found it frustrating to think about, planetary nebula, thousands of them, open clusters, thousands of them, variable stars, thousands of them, globular clusters, 160, a nice manageable list. And so I took the list, and, most lists would be given in terms of increasing right ascension, which just basically means you'd have to follow them around the sky. And I thought, no, let's rearrange this in terms that a developing amateur astronomer might actually find useful. And being in astronomy, of course, we have to have really ridiculous names and categories for things. So I decided to call them early, punctual, fashionable, and late. And that means nothing except it's on my list that way. So the early class here are the globular clusters that are really bright and easy to see. And basically, you can pick them up even with a small telescope. You'll note I have NGC 5139 at the top of the list. There's a reason why it's at the top. That is, of course, Omega Centauri. And I'd like to say a few more words about that a little later as we go on here. There's about 40 in that list. And then the punctual list requires a little more. Either with a small telescope, you got to be skilled, or you get a bigger telescope, and then you can develop your skills that way. And then the fashionable list will be a challenge for just about anybody in amateur astronomy. The globular clusters on the late list are almost impossible to see with an amateur telescope, even 40 centimeters or larger, simply because they were discovered, most of them are discovered behind dust clouds, so their light is reddened, and they are very dim to visible light. And the ones that many of them are on that list there. And I think that might be interesting in the coming years that the James Webb Space Telescope will actually be able to observe these, the ones that are deeply reddened. So there might be some news coming out of that. So I haven't even really made much of an effort for the ones on the late list, but I've tried to observe any of the ones on the other three lists, and it's a really good challenge for you as an observer. Well, one of the things folks often ask about globular clusters is what would it look like if you were in a globular cluster. And so Arthur C. Clarke is known as both a science fiction writer and a science writer. And he wrote a passage in this book called The Exploration of Space, in which he gave quite a poetic description. I didn't repeat the whole thing here, but he does sort of make the mistake of saying that, the sky would be literally as bright as day because of all these stars. And that turns out to not to be true. A writer named Anatoly Boyko in November 1964 analyzed the situation and wrote an article for Sky and Telescope in which he said, no, what would happen is the night sky wouldn't be truly black inside a globular cluster, but you would have sky. And then there you'd see something like a few thousand first magnitude stars. So, and stars that are brighter even than that, even up to the brightness of Venus would be the ones that are closest to you. So you can imagine what it would like to have a few thousand really bright stars in our sky and then not have a really black night behind that. That would be really kind of cool. And so that's an image that folks like to think about. Back in the 1980s, I thought it would be kind of cool to look at how these things are actually, what they actually look like. And of course, 1980s computers, you could do some fairly basic pixel generating image programs. And so Sky and Telescope had a small program. I'm pretty sure it was written in BASIC language, if I remember correctly. And so you could just have this generated on your screen and make a little image of something. At least it shows that a simple model of, greater probability of a dot being at the center gives you something that looks like a globular cluster, which again gives a hint as to something about the physics of the situation. In this little YouTube video, more recently, let's see here, where's my mouse? There we go. The researchers who did this have actually done a simulation, imagining that you might have a big group of stars randomly located and how they would all gradually converge into a cute little globule. And then that globule would rebound and gradually kind of disperse, but the dispersion can actually take a very, very long time. So in fact, the globular clusters are in fact among the most stable objects in the universe. The globular clusters are, some of them are as old as the earliest observations that we can really make in astronomy. So there's a lot of neat things to learn about the process. I'm going to stop this and move on to the next slide. The next slide has a shorter simulation, but it also basically shows the motion of randomized star velocities, and it just gives you a sense of how individual stars move in a globular cluster. They don't go on regular orbits the way a planet would go around the sun. They're moving not at random, but they're moving as a result of gravitational forces, but they have these motions going in and out through the center, and there's all these complex patterns that the folks who study the dynamics of globular clusters have been analyzing, well, now, for 100 years now, but even just in recent years, they've been able to simulate these much better and learn a lot more cool stuff about them, which I find really fascinating. And part of that then becomes the astrophysics of it. And I have to admit, when I was an undergraduate, I kind of dreamed that this would be the stuff I would study. The idea that having a group of stars all located more or less in one place, and astronomers presumed, going back 100 years now, that not only are they located in a globular cluster together, but that they were all the same age in that cluster. And so differences in the stars that we see are not due to different ages, but rather due to different processes. Now, it's gotten more complicated in the 1970s and 80s, and since then, they now realize there are different populations of ages within an individual globular cluster, but it's still a useful idea to study the evolution of stars within a single cluster. And so the previous picture showed M5 the way it would look in your telescope, but this shows M5 the way it would look if you put it on a graph, where on the horizontal axis, we've got the color of the stars, where the color is technically defined by measurements. And on the y-axis, the vertical axis in the diagram here, is the actual brightness, how much light the star actually emits. You can definitely see that there's not a random shape here. They're not all over the map, but you can definitely see that they're not a globule anyway on this graph. Why would you expect them to be? The most of the stars are in this sort of diagonal line down towards the center in the lower half. That, of course, is the famous main sequence that we see in stars generally. But the idea is that all these stars have gone through different processes as they age, and they're different kinds of stars as they age through that. And you can tell from the shape of this graph how old of an object Messier 5 is. So these lines, there you see the same structure with the main sequence in the lower center, and all these little lines that have been drawn here, each globular cluster will seem to follow a different one of those lines, telling its age. So most of the globular clusters are up around 9 or 10 or 12 billion years old, but we can tell which one is a little older and which one's not quite so old by looking at these diagrams. These are these tracks, as they're called, are the main tool for analyzing this stuff for globular clusters. And I find that a very fascinating way to kind of wrap up really all of astronomy. And even though stars are everywhere and we observe them all over in all kinds of categories, our understanding of them has very largely come from studying them in these little concentrated laboratories of the globular clusters. And so I would like to summarize for you. Why do I love globular clusters? I hope I've sort of given you some ideas on each of these topics. I think they're beautiful. You can see them without fancy photographic techniques. They look great in small telescopes. The list of having 160 of them, of which, you know, even as a beginner, you could try to observe 40 or so of them. We figured out what role they've had in philosophy of our understanding of the universe. I've got great memories attached to them, the stories that I've told. They certainly help in studying stellar evolution. The dynamics of the stars inside those things are really pretty cool. And then, of course, there's the question of the cosmology. You know, I just listened to a talk basically yesterday called Early Formation of Galaxies in the Universe. Person was talking about, you know, how galaxies formed after the Big Bang, after the early dark ages. And I thought to myself, that's exactly the kind of research that, as more work is done, is going to gradually bring in the role of the globular clusters as the galaxies develop. And I think that's going to be really neat in the coming generation. And finally, globular clusters have been mentioned in exciting science fiction stories. And that is why I love globular clusters. Thank you for your attention this evening. It being Zoom, you know, I don't get to see you all giggling away at all my great jokes and things, but I'll take it for granted that you're all howling with laughter out there in Zoom land. And here's a long list of folks that I've consulted with or had helped me over the years and have loaned me their slides or have given me advice and so on, been with me on trips. And so thank you very much. I'll take questions.
Go ahead, Brian.
I wonder why globular clusters don't have any sign of rotation like a galaxy does.
Okay, can I just repeat that, make sure that everybody heard that? So the question is, why don't the globular clusters have a sign of rotation like galaxies have? Okay, Peter, can you help us with that?
Yes, I can give at least a sketchy answer to that. It's a good question, and I could give a really long answer based on the idea that a galaxy, after all, rotates not as a solid object, but all as an object. And so it all rotates and it has an axis and it goes around that axis. Globular clusters really don't do that because the stars in them are all they are. And the stars in them are moving in and out and around and back. So they don't really have an overall rotation. Now, if we studied them closely enough and found that on one side, more of them were coming towards us, and on the other side, more of them were going away from us, we might say that overall there was a general rotation to it. But my understanding is that when you do those kind of studies, the statistics don't lean you to take it for granted that the whole thing is rotating as a single object. So that's my understanding of it. I hope that I'm pretty sure I understood that that was the question. That's what the question was about.
Brian's follow-up question.
Oh, okay, go ahead, sure.
I'm just wondering whether there was a stage in galaxy formation where the stars had the same more random motion like we're seeing in the globular clusters.
Okay, so just to make sure that everybody has heard that, the question is, was there a stage in galactic evolution when the galaxies had that same sort of non-specific kind of type of dynamics?
Yeah, I don't think I should answer either yes or no. My sense is that the earliest phases of galaxy development, the structure of how galaxies became spirals, is still the thing that they're trying to push back and understand, because it would have happened right soon after the molecules and so on became available. So something like a few 100 million years after the Big Bang. Now, since then, of course, not to get off my topic, but galaxies, of course, nowadays, the spiral structure is almost always due to an interaction of one galaxy with another. So if you take two giant elliptical galaxies and simulate their motion together, and as they come and go around each other and separate apart, they both turn into spiral galaxies. So in fact, it may well be the case that no galaxies started off as spiral galaxies, that they all started off as giant elliptical galaxies. And you might then say that perhaps future research will prove that, in fact, the development of giant elliptical galaxies is analogous to the development of smaller globular clusters. It's funny to call them small when they're as huge as they are. But it could be that we're talking about a size range that goes from what we now think of as globular clusters that just happen to still be independent, all the way up through mid-sized objects, which are dwarf spherical galaxies. And I was going to mention, I figured it would come up in the questions, NGC 5139, Omega Centauri, is no longer really considered a globular cluster, because it is now, the measurements show that it looks more like a dwarf spheroidal galaxy. And so it may be exactly what we're talking about, a sort of a medium scale example of this category of object, which then goes up, many, many more factors of 10 to become the giant elliptical galaxies, which then interact to become spiral galaxies. If it turns out that that's correct, then of course that puts the globular clusters kind of at one end of a very critical range of sizes of objects that are important in the structure of the universe as a whole.
Now, a question from the chat group is, are globular clusters the core of old galaxies?
Also an interesting question. And the short answer is no. And it's pretty certain that they are not. For the most obvious reason is almost every galaxy, I think I can say every galaxy that's been studied in this way is now known to have a massive black hole at the center, and globular clusters do not. So if we could see something that was the core of an old galaxy, it would have a large, supermassive black hole at the center. Globular clusters don't have that. So in fact, it's more likely that it's the other way around, that galaxies are some kind of either a growth process of globular clusters. And so in other words, galaxies are really the old children or products of globular clusters. Galaxies are the products of globular clusters, or perhaps many globular clusters merging together, gradually building up to the point where then they become an elliptical galaxy. So yeah, that's a more thorough way of looking at the question. Globular clusters do have some examples of black holes, but they have not. If there were a supermassive black hole in any of the Milky Way galaxies, globular clusters that have been observed in this way, it would have been fairly obvious, because they would be so huge they would just start swallowing things, and the dynamics would make it obvious.
Okay, another question from the chat is, a personal one to you, Peter. Have you studied the globular clusters in the Andromeda galaxy? There are several visible from the Earth in amateur scopes.
Right. And that's a really sharp question to ask a guy like me, because I've never really thought of myself as a really skilled observer. I like trying to develop my skills, and I'm certainly better than I was 30, 40, 50 years ago. But I've never been able to pick a globular cluster in the Andromeda galaxy out from either individual stars in the foreground or something else. Maybe it's a nebula or something. And so I'd like to suggest that really only the really best observers can tackle the project of starting to identify the globular clusters in the Andromeda galaxy. Now, of course, professional researchers know the Andromeda galaxy has at least 600 globular clusters. So it's got quite a significantly larger family of globular clusters than our Milky Way has. Unless, of course, it turns out that there's another 400 globular clusters on the other side of the bulge of the Milky Way that we just simply haven't seen, which that would be pretty unlikely that they would be, all stuck on the other side like that. So for reasons that I presume are simply random chance, as the galaxies developed and so on and so forth, the globular clusters, just more of them happen to gather around the Andromeda galaxy. There's only about 3 or 4 of them that I've heard mentioned as being visible in modest amateur telescopes, and I've never made the effort to. If you do pick one out, it's going to look pretty much star-like, simply because you're not going to be able to make out the globular cluster detail that we can enjoy when we look at the globular clusters in our own galaxy.
May I ask a question?
Okay, just a sec, Erwin, or if there's now a question from the live audience. So was it Merv?
Yeah, I was just wondering, with the pattern the stars have, is there a lot of collisions over the billions of years? You think it would be quite a bit of
Okay, so the question is there a lot of collisions over the billions of years that these globular clusters have been in operation, with the stars moving around the way they do?
Right. Yeah, there's 2 important things in order to answer that question. First of all, is we tend to, especially those fictional representations of globular clusters, or the Arthur C. Clarke one that I mentioned, tend to kind of pack the globular clusters in as if they're kind of like, they're in there shoulder to shoulder and, cheek by jowl, but that's not the case. The average distance between stars in a globular cluster is still, more than a light year, something like on average 3 to 5 to 10 light years apart. And so there's still plenty of room between the stars. And so then the sort of flip side of that is that you think, oh, well, if there's that much space, then chances are collisions are actually quite rare. But in fact, in recent years, since I was an undergraduate, sometime in the 1990s or so, there's certain categories of spectral observations that make certain stars in globular clusters look bluer than the theory would predict, and bluer than the rest of them in that globular cluster. And folks wondered about this for a while, and somebody finally came up with the idea that, in fact, these stars in globular clusters that look bluer than they are supposed to are actually stars that have had, let's not call it a collision, but let's say a close encounter with another star, and had some of their mass then ripped away from them. So actual collisions are still thought to be quite rare, but collisions in the more vague sense of interactions where they get close enough to, swap some mass or rip mass off each other, that is now seen as being the explanation for this category of stars that are too blue to fit the more standard categories.
Thank you.
Did that sound reasonable?
Yeah.
That helped me?
Now, Erwin, did you have a question?
Just to go back to the idea of the ontogeny of globular clusters, surely one could imagine that there had to be a giant gas cloud which would begin to condense, and as this happens, it would automatically start to rotate. And if that giant gas cloud eventually results in, a few 100,000 of suns, surely people must have tried to simulate such, starting with a giant gas cloud beginning to rotate, and so it should end up with a globular cluster that as a whole would have to rotate.
Right. So I think the reason it's kind of not seen that way is the globular clusters being as old as they are, they must fit in somehow with explanations about these gas clouds in the earliest parts, earliest time of the universe before the current galaxy interactions all occurred. You know, the Milky Way's had some interaction in the past, and we see all these galaxy examples in the sky that are interacting even now as we watch them. But, you know, the globular clusters must have been around not too long after the first stars formed, and maybe even before the first galaxies formed. That's where I get the idea. So the original gas clouds that would have been in that early universe, so we're talking about something like maybe 400 million years after the Big Bang, that gas cloud wasn't rotating, the whole universe wasn't rotating in a particular direction where we would all get the same angular momentum and all be turning in the same direction. Instead, what happened is that the gas clouds started to form themselves into filaments. And wherever the filaments kind of crossed, they formed these kind of knot-like things. And you've probably seen these simulations now that show this the structure of the early universe like this, and galaxies then formed along these filaments. The filaments were so vast that they're big enough to basically let galaxies form within them, and in the gaps between these filaments, we call them voids, and there's like literally, well, not quite nothing, but there's less in these gigantic voids than there is, you know, in our galaxies, and from one galaxy to the next. And the galaxy clusters then arose out of that. And in fact, those filaments formed as a result of what probably were quantum fluctuations in the original Big Bang, at the moment when atoms, when electrons and nucleuses were able to fit together. And that, of course, is the moment of the cosmic microwave radiation that we see. That famous mottled picture that's been improving over our lifetimes, the last 20, 30, those fluctuations are thought to have turned into the filaments along which the galaxies form. So the step that's missing, if it's true, is that how did those filaments then give rise either first to globular clusters and then galaxies, or give rise to both globular clusters and galaxies together, one or the other? And I don't think we know that yet. I think that's still an active discussion point.
Well, thank you.
I like how you used the word ontogeny, by the way. That was good.
Okay, are there any other questions? Any
Yes,
other
I would have one more question as to planets. Is there any indication that any of those stars in a globular cluster could have planets?
All right, fair enough. Of course, it's a star. Stars form out of gas clouds, much smaller gas clouds than the ones we were just talking about a second ago that basically give the whole structure of the universe. But when a star forms out of a gas cloud, that gas cloud is rotating. And that rotation ends up in the rotation of the star, and also in the rotation of the gas around it that's left. And then that ends up determining, or maybe determining is too strong a word, it's influencing the formation of planets. So that probably happened in globular clusters as well. But the key thing for us to realize is that all of this wonderful talk about the discovery of exoplanets and the Kepler Space Telescope, all those wonderful measurements, you know, those thousands of exoplanets that are now known are all within a few thousand light years of our solar system. and the very nearest globular cluster is too far away to fit into those observations.
Yeah, okay, yeah.
So we have not been able to see any kind of observational evidence of the presence of planets in globular clusters. Now, maybe the transit method, which as you probably know, if a planet happens to pass between us and the star that's right next to it, we can kind of measure that dip in brightness, even though it's a very small dip in brightness. That as the transit method gets better and better, right now they're routinely observing, even amateur telescope equipment. You know, Rick Wagner, our RASC remotely operated telescope in California, even equipment like that can measure quite reliably to within 1/100th of a magnitude. If we can get down to 1/1000th or even 1/10,000th of a magnitude, maybe we'd be able to see the variations in transits in globular clusters. So that might be a place where we would have luck in the future, success in the future.
Thank you.